Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. This is section 11.4 and it's about comparison tests. And I will talk here about one of the comparison tests, which is the direct comparison test. The direct comparison test says that if we have two series, summation an, summation bn, and these two series have positive terms, so all the terms a1, a2 up to infinity and b1, b2, b3, all of them are positive. And if summation bn is convergent and an is less than or equal to bn for all n, then summation an would be also convergent. Notice that an is less than bn and summation bn is convergent. So if an is less than bn, then summation an would be also convergent. So it says less than convergent is convergent. If there is a series with infinite sum and it is convergent, so this infinite sum has a limit, then anything less than that would be also convergent. The second part, if summation bn is divergent and an is greater than bn, then summation an would be also divergent, because here summation bn is divergent and an is greater than bn. The greater than divergent would be also divergent. Divergent means go to infinity. The infinite sum will go to infinity. If the infinite sum of bn goes to infinity, then anything greater than that will also go to infinity. So less than convergent is convergent, greater than divergent is divergent. Now, usually in the question, summation an is given. So this is an, okay? But how to find bn? So we need to find summation bn. And summation bn usually has to be either a p series, so in the form 1 over n to the power p, or a geometric series in the form a times r to the power n minus 1. Because we know that the p series converges if p greater than 1. If you need more information about p series, watch section 11.3. And geometric series, if absolute value of r is less than 1, it would be convergent. And we discussed that in section 11.2. So determine whether this series converges or diverges. First thing to think about is an positive. Look to the terms. All of them, if n is 1, notice that n from 1 to infinity, 1, 2, 3, 4, up to infinity. So it is clear that an is greater than 0 for all n greater than or equal to 1. So we have positive terms, okay? The series has positive terms. Good. So we can apply the direct comparison test, but we need a series summation bn. So how to determine bn? You always determine bn by taking the term with the highest power in the numerator in an and the terms with the highest power in the denominator. So this is bn. And we need to compare now an to bn. Well, what do you notice about bn? Well, this is 5 over 2 n square. We know that summation 1 over n square is convergent p series because p is equal to 2 and it's greater than 1. So 5 over 2 times summation 1 over n square is also convergent because it's a multiple of 1 over n square. So Bn, summation Bn is convergent. So we need to compare now summation An with summation Bn. Summation An would be convergent if An is less than Bn, because less than convergent is convergent. So what we need to prove that, we need to prove that 5 over 2n square plus 4n plus 3, which is An, that it is less than 5 over 2n square, which is correct. Why it is correct? Because here in the denominator, we are making the denominator smaller. Notice that everything is positive, n is greater than 1. So 4n plus 3, this is a positive number, and we are removing this number from the denominator, so we are making the denominator smaller. So if you have 1 over 3 over 4, for example, and you want to compare it with 1 over 3, of course, this is less than 1 over 3 because you made the denominator smaller. So this is correct, this is true. Then by direct comparison test, summation an is also convergent. Here, use the direct comparison test to show that the first series converges by comparing it to the second series. Well, we know that this series is a convergent P series because P is equals to 2 greater than 1. So if we can prove that AN, this is AN, and this is BN, if that AN is less than BN, then this series would be convergent by the direct comparison test. So what let us consider n over n cube plus 5. Okay, if we remove 5 from the denominator, then this would be less than n over n cube because we are making the denominator larger. Uh, sorry, smaller, so the fraction is larger. And n over n cube is 1 over n square. So an is less than bn. So by direct comparison test, summation an is also convergent. Use the direct comparison test to show that the first series uh, diverges here by comparing it to the second series. What is this? This is the harmonic series. It is also a P series with P equals to 1. So it's divergent. So if we want to compare summation an with summation bn, we know that summation bn is divergent. So we have to prove that an is greater than bn because greater than divergent is divergent. So let us start comparing an. Let us write it greater than something until we reach 1 over n. Well, now n cube minus 2. So if I remove minus 2, I am making the denominator larger. So this fraction would be greater than this. So if you have 1 over 5 minus 2 and you want to compare it to 1 over 5, well, this is greater than this because this is 3. 1 over 3 is greater than 1 over 5. Okay. And now I have n squared plus n in the numerator. So I can write it greater than n squared over n cubed. Because if you have 4 plus 3 over 7, of course, this is greater than 4 over 7, isn't it? So n squared over n cubed is 1 over n. So by direct comparison test, summation an also converges because summation bn, sorry, diverges because summation bn is divergent. So, and an is greater than bn, so summation an is also divergent. Which of the following inequalities can be used to show that this series converges? Well, to show that this series converges, I have to write it. I have to write an. This is an. I have to write an n cube plus 1 less than convergent bn. Okay, convergent series. So greater than is not good. Less than 1 over n is not good because this is divergent. But this one is the correct choice because n over n cube plus 1 is less than or equal to 1 over n square, and 1 over n square is convergent. So we can use this inequality to show that this series converges. Which of the following inequalities can be used to show that this series diverges? I have n over n square plus 1. If you want to prove that it is divergent, you have to prove that it's greater than divergent series. So less than is not good. Greater than 1 over n square is not good because this is convergent. But greater than 1 over 2 n, that's the correct choice because 1 over 2 summation 1 over n is a multiple of the harmonic series, and it is divergent. Determine whether the series converges or diverges. Okay, here you don't know. So this is an, and I need to determine bn. But first, I have to make sure that an is positive, greater than 0 for all n greater than or equal to 1. So it has positive terms. And now let us determine bn. bn is 1 over n cube, highest power over highest power. And what is this? This is a convergent P series because P is 3 greater than 1. And now an, which is 1 over n cube plus 8, is less than 1 over n cube because I removed plus 8. And an is less than bn, and summation bn is convergent. So by direct comparison test, summation an is convergent. Again here, same method. First, check that an, this is an, put n1 so it's always positive for all n greater than or equal to 1. Let us determine bn. Highest power, and there is only one term here, so it's 1 over square root of n. This is a divergent P series because P is half less than 1. So now we need to prove that summation an is divergent. So we have to show that an is greater than bn. So this is an. It is greater to what? We can remove the plus 1 because we have seen that 2 plus 3 over 7 is greater than 2 over 7. So, and here we can cancel and we get 1 over square root of n. So this an is greater than bn. So by direct comparison test, summation an also converges. I mean diverges. Greater than divergent is divergent. An, put n1, you get 0. So an here is greater than or equal to 0 for all n greater than or equal to 1. Well, what is Bn? Term with the highest power, term with the highest power, 1 over n square. This is a convergent P series with P equals to 2 greater than 1. So we need to show that An is less than Bn. N minus 1 over n cube plus 1. This is An. I need to remove the 1, this one, from the denominator. I'm making the denominator smaller. 1 over 2 plus 1 and 1 over 2. This is less than, isn't it? So this is less than n minus 1 over n cube plus 1. Oh, plus 1 will be removed. And now, what about 2 minus 1 over 3 and 2 over 3? Okay, this is 1 over 3. It's less than. So I can say less than n over n cube. And this is 1 over n squared. So this is the proof that an is less than bn. And hence, by direct comparison test, summation an also converges because summation bn converges and an is less than bn. Notice here that no p series anymore, but this is a geometric series. 9 to the power n is a geometric series. But this is an, and again I can see that it is always greater than 0. If you take n1, it would be positive greater than 0 for all n greater than or equal to 1. So what is Bn? Well, when n goes to infinity, think of the important terms here. 3 is a number fixed, but 9 to the power 1000, 10 to the power 1000. So these terms really controls the fraction. And this is 9 over 10 to the power n. And this is a geometric series with r equals 9 over 10 less than 1. So it's convergent. Now we have to show that an is less than bn because bn is convergent. So 9 to the power n over 3 plus 10 to the power n. Can I write it less than 9 to the power n over 10 to the power n? And yes, because I'm removing 3 here. So summation, and this is 9 over 10 to the power n. So by direct comparison test, summation an also converges. Okay, you can say that summation 9 over 10 to the power n is a geometric series. All right. Here, if you put n1, this is positive, so n greater than 0 for all n greater than or equal to 1. This is showing that all the terms are positive, because if the terms are not positive, you cannot use the direct comparison test. Well, this is an. What is bn? 6 to the power n over 5 to the power n. And summation 6 over 5 to the power n is a divergent geometric series because r is 6 over 5 greater than 1. Okay, so bn, summation bn is divergent, so we have to prove that an is greater than bn. So 6 to the power n over 5 to the power n minus 1. Is it greater than 6 to the power n over 5 to the power n? Yes, because this is minus 1 and we removed it. So by comparison, by direct comparison test, summation an also diverges. Well, here sine square k, when k goes to infinity, sine square k is always a number between 1 and 0. So it doesn't increase when n increases. But look to k and k cube. So Bn here would be k over k cube or 1 over k square. And this is bk, okay? So this is convergent. Then you can say that summation 1 over k square is a convergent P series because P is 2 greater than 1. So now this is a convergent series. We have to show that AN or AK is less than BK. So K sine square K, and you have to prove that. You have to show it step by step. I can remove the 1 from the denominator, and this would be less than because I made the denominator bigger, larger. And we know that sine square k is less than 1, so I can write it less than k over k square. This is a cube. This is 1 plus k cube. And k over k cube is 1 over k square. So by direct comparison test, summation an also converges. This is an. We know, well, ak again. We notice that ak is greater than 0 for all k greater than or equal to 1. Here also. Okay. So what is bk? Well, bk would be the term with the highest power, the term with the highest power. This is k to the power 1 over 3. This is k to the power 3 over 2. 3 over 2 minus 1 over 3 is 7 over 6. Now summation 1 over k to the power 7 over 6 from 1 to infinity is a convergent P series because P is 7 over 6 and this is greater than 1. So now to show that summation AK is convergent, I have to show that AK is less than BK. You can write AK equals, okay? Notice that k cube plus 4k plus 3 plus positive numbers. So this would be less than if I remove these positive terms from the denominator. I made the denominator smaller. And this is 1 over k to the power 7 over 6. And this is bk. So ak is less than bk. So by direct comparison test, summation ak also converges. Notice that here cosine n is sometimes positive, sometimes negative. put cosine 2 in the calculator, radian mode. So cosine n is between 1 and -1. But so if there is no 1 here, we will not be able to use the direct comparison test. But there is 1, he added 1, so 1 minus 1 is 0, 1 plus cosine n. So actually 1 plus cosine n is between 0 and 2. And because of this, so 1 plus cosine n is positive, en is positive. So an is positive for all n greater than or equal to 1. What is bn? When we go to infinity, cosine n is not important because it's a number less than 2. So I have 1 over e to the power n. Notice that summation 1 over e to the power n when from 1 to infinity is a geometric series with r equals 1 over e less than 1. So it is convergent. And now we need to prove that an is less than bn. So an 1 plus cosine n over en. We know that 1 plus cosine n is less than 2, so I can write it less than or equal to 2 over en. So, of course, 2 over en would be also convergent because it's a multiple of 1 over en. And this is 2 times bn, can say like this, okay? So, by direct comparison test, summation an is also convergent. Well, here, if you choose n1, 3 minus 2 is positive. So an is greater than 0 for all n greater than or equal to 1. What would be bn if this is an? It would be 4 to the power n plus 1 over 3 to the power n. And notice that summation 4 to the power n plus 1, I can write it 4 times 4 to the power n. And then I can write it 4 over 3 to the power n. So this is a geometric series with r equals to 4 over 3 greater than 1. So it's a divergent geometric series. So I need to show that an is greater than bn. Well, notice that an is 4 to the power n plus 1 over 3 to the power n minus 2, and this is negative. So this is actually greater than 4 to the power n plus 1 over 3 to the power n, which is bn, because we removed the -2. So we made the denominator a larger. So now this is greater than this. So by direct comparison test, summation an is also divergent. Notice here in this exercise, this is an, and an is always positive. And bn here would be 1 over n square. And the reason because n to the power n is greater than n to the power 2. If n is 1, greater than or equal, okay? If n is 1, so 1 to the power 1 would be equal to 1 to the power 2. If n is 2, 2 to the power 2 would be equal to 2 to the power 2. After that, n to the power n would be greater than. And this is convergent P series, or you can write that summation 1 over n square is a convergent P series because P is 2 greater than 1. And 1 over n to the power n is, since n to the power n is greater than n square, then 1 over n to the power n would be less than or equal to 1 over n square. So by direct comparison test, summation an is also convergent. Now, let me tell you something. That's the end. I'll stop here. Enough exercises about this test. But let me tell you something. N to the power n is also greater than or equal to n to the power 1, isn't it? But hence 1 over n to the power n would be less than 1 over n. Now, is this useful? Is this useful? Is this information useful to use the direct comparison test? And the answer is no, because 1 over n is divergent. Less than divergent, we know nothing about it. The direct comparison test says if you want to compare with the divergent, you have to prove in 1 over n to the power n is greater than, not less than. And that's why we used n square here, because 1 over n to the power n is less than or equal to 1 over n square. Well, this is the end. Thank you very much. Hope you enjoyed the direct comparison test.